There is no point explaining how transformers change the world we live in today, from generating text in natural languages to start understanding emotions through text and images that no one had thought would possible 5 years ago. Initially, the transformers are designed by the team at Google to improve language translation quality, but their attention mechanism seems to have more potential than understanding natural languages. So, few researchers saw the potential of transformer and modified a bit to try and see if they understand images as well, and the results were astonishing. Till 2021, convolutional neural networks were the de facto standard for image processing, classification, detection, or whatever related to images. But when this bomb was dropped, everything was changed forever. Because transformers outperformed CNNs at image classification tasks at medium and large scale and proved that they can dominate the domain of image processing as well. The world knows these kind of transformers as vision transformers. Let's understand how they work. But before getting on to vision transformers, you need to understand why CNN performed so well since 1989. So CNN works so well due to its inductive biases, which refers to built-in assumption or prior beliefs about the kind of pattern it's going to encounter in the data. Now remind you, this is before even training has started. So these are some of the biases which make CNN so good. The first one is the bias about locality. To understand this, let's take a closer look at this example image. A little more. A little bit more. Yes, perfect. Now, take a single point in the image for now and see the pattern that every other neighbor pixel is either of the same value or closer to the origin value. And no matter where you look in the image, you'll find a similar pattern. So this is the bias that even without looking at an image, you can say that every other pixel near a pixel will either be the same or closer in intensity. The second bias is translation invariance. These consist of two things happen in CNNs. First, weight sharing. So we know filters are applied across image. So if that filter learn to recognize a curve in a part of image, then it doesn't matter if a curve located at any other part of the image, the filter will still recognize that as well. In summary, the pattern will be detected no matter where its location in the image. Second, pooling layer. This reduces the spatial resolution by summarizing nearby activation. This makes the network less sensitive to small shift or distortion in the image. The third bias is about spatial hierarchy. We know that the CNN made up of stacking multiple layers where lower layers learns basic patterns like edges, corners, or textures, then the middle layer learns to detect part of the image, and similarly, higher layer learn to recognize the objects in the image. That's inherited in CNN no matter how deep or shallow the network will be. The layer will learn the same pattern in the same way irrespective of data or training mechanism. So due to these kind of biases, CNN performs extremely well on images. When it comes to vision transformer, there are no such inductive bias, and that is the reason it converges late due to learning those patterns initially which already inherent in CNN by birth. So how do vision transformer process images? We know that traditional transformer takes a sentence, then add positional embedding to retain the information about position of each word and then performs attention mechanism. Knowing working of transformer is essential to work on images. The link for how transformer works in detail is in the description. Please watch that first in case if you don't know. Now take an image, split it into patches, then get linear projection of flattened patches and attach position information by adding positional embeddings. So these are now a numerical, or I would say vector representation of the images. Now before feeding these to encoder, we add something we call classification token, represented by CLS. It's a learnable vector that prepends to the patch sequence. During self-attention, it interacts with all other patches. By the end of the transformer layer, it contains a summary representation of entire image. Then these embeddings get through encoder where attention gets computed. One thing I want to mention that we don't have the decoders just because decoder takes internal representation from encoder to generate sequence of text. Because we are not generating anything here, we need encoder only to get the internal mathematical representation of input, then pass it through a classification layer to get the classification result. That's it. That's the whole architecture of vision transformer, and now you know how it works. So what's next? If you truly want to learn everything about it, then make it from scratch. So what are we waiting for? Let's make it. But before getting too eager to put your hands on keyboard and start coding this, let's understand the equation which explains about the architecture. This will guide us to implement ViT. So there are four equations mentioned in the paper. Equation 1, which is embedding patches, is equals to embedding patches plus positional embedding will be added with the classification token attached, where embeddings is equals to linear projection of patches and positional embedding will be the number of patches times dimension of embeddings. But since we are adding one more classification token, so n plus 1 will be here. Then each transformer layer update its input by applying layer normalization, multi-head self-attention, and then adding the original input via residual connection. Then output from encoder will go through multi-layer perceptron, where each layer refines its representation by applying layer normalization, passing it through a multi-layer perceptron and adding original input via residual connection. And then finally, you will get output y by applying layer normalization to classifier's output. So these four equations makes vision transformer. Don't worry if you don't understand or get these equations perfectly. Things will be clear once we start coding the architecture using these equations. So are we ready to implement this? Yes, but before that, here are the requirements. So without getting further ado, let's get started. First, import all the necessary ingredients which will make up our ViT recipe. Use CUDA engine if NVIDIA GPU is available. Now get the dataset. For this task, we are going to use Cypher10 dataset. But before that, let's compose a transform to pre-process and normalize the images with a little bit of augmentation for better generalization. Load both training and test set with transform for pre-processing and use data loader with batch size that your memory can handle. You can build a function to visualize the sample of the dataset if you want. It's augmented data, which comes right after pre-processing. That's why you can see black or empty part in the images, as well as some images are flipped randomly. The images are ready now. To make a function to split into patches, the unfold function will help us out splitting the image into 2D patch of 4 by 4 pixels. Then flatten the grid of patches into one dimension tensor and rearrange the tensor. Here's a formula by which you can compute the number of patches given the image size and the size of patches. For example, a 32 by 32 image with 4 by 4 patch would split in this number of patches. You can make a function to visualize the patches of the image. First, split the image into patches, then pass the image and patches to the function. And see, these are the 4 by 4 patches of the input image. And now we have the dataset, data loader, and a function which splits the image into patches are ready. And now let's work on building embeddings and model. A truncated normal keeps the initial weights within a set range, avoiding extreme values that can slow or destabilize training. This leads to more stable gradients and faster convergence in neural network. Now, let's build the patch embeddings. Initially, all necessary variables makes a linear layer to get linear projection of patches, which is the part of the architecture, and initialize its weight with our weight initializer, and set the bias with 0. During forward pass, make sure you get a perfect square image and then split the image into patches in the same way we did in patchify function. Then pass the patches to linear layer to get projection of embedding size. And this will be your embedding of patches. Let's pass a single image through patch embedding layer and print the resulting patch embedding shape. Make a function if you want to visualize each patch embedding from tensor by reshaping and displaying them as a colored strips. It loops through all the patches in the first image of the batch and plot them using matplotlib. The scale parameter controls the size of displayed embeddings. And here are the patch embeddings. I know it appearing very small, but they are actually smaller than what they are appearing. And you may say vertical line in each patch. Now make a module to add positional encodings to input embeddings to retain the sequence order. We know that sinusoidal waves are used to generate positional information, and in forward pass, we add positional embeddings to input tensor. Now we have both patch and patch embeddings. Let's build the embedding layer for transformer. Create a learnable class token as mentioned in the paper to prepend the patch embeddings. Initialize learnable positional embedding for all patches plus the class token. Adds dropout regularization to prevent overfitting. Initialize both class token and positional embedding with our weight distribution function. The forward pass process input patch embeddings by prepending a class token and adding positional embeddings. Then apply dropout and return the output. And now we have completed this part in the figure and equation 1. Now let's make encoder block. The breakdown of encoder mentioned in the paper is similar to the original transformer. So let's see how this equation looks in code. Make encoder module and make layer normalization. Initialize multi-head attention with input embedding dimension and number of head. And then make a dropout layer. If you see the breakdown, then we have two layer normalization layer. So let's make the other one. This will normalize input before sending it to classifier. Now make our classifier. You can experiment with different number of hidden layer or units, but for now I am going to stick with what mentioned in the paper. Now decide forward pass according to the equation. We know input will pass through layer normalization first, then its output will become input of self-attention layer, and this represents residual connection of original input. So this is the equation 2, but we are not done yet. We need to implement this equation as well as this part of the breakdown figure. This output will again pass through a layer normalization and then get through classifier to produce output and add original input as residual connection. I'm skipping equation 4 because it's not necessary. It's just passing the output from classifier to another layer normalization layer to produce output. And finally, add the residual input to classifier and return the result. Now we can use this encoder block to make transformer. Define image size, path size, dimension of channels, dimension of classes, dimension of embeddings, depth, which is the number of layers, attention head and all. Now initialize patch embedding with all the required parameters and the number of patches we get from input image. Define our transformers embedding, the one which contains extra class token with all required parameters. Now linearly stack the encoder blocks till depth of the network. Define layer normalization layer and linear layer and initialize linear layer with our truncate normalization function and bias to 0. In forward pass, get the patch embedding and get the embedding which contains class token. Pass the embedding through encoder block and get the embedding of class token from each sample of the batch. This contains global information about the image which can be used to classify the input. Normalize it using layer normalization and pass it through classifier to get the logits. Let's test it. Initialize the above transformer with all required parameters according to the dataset. Get a sample and expand its dimension by 1. Now feed the input transformer and print the output shape. This is an optional step, but I still want you guys to do it to get a detailed image of transformers architecture. We will use TorchWiz library to make a visualization architecture of the model which will show all the operation in graph format. See this image? It contains every single operation to be performed in form of graph. And these are the residual connections we made. Now one final thing before training transformer is define a learning rate scheduler, which starts with warming up linearly, then decays as cosine curve, which is a common trick in training transformers. The function takes an optimizer, number of warming steps, total training steps, and a minimum learning rate factor. And this is warm-up phase where the learning rate increases linearly from 0 to base learning rate. And now return cosine decay phase after warm-up, which makes learning rate follows a cosine curve from the base learning rate down to minimum learning rate by the end of training. Warm-up prevents unstable updates early in the training, and cosine decay helps the model converges smoothly without abrupt learning rate drops. Now make the function to train transformer. Define function which takes model, training, and validation set, the device you are using, number of epochs, learning rate, weight decay, and warm-up ratio. Set up loss and optimizer. We'll use Adam optimizer with weight decay. Make optimizer gradually increases learning rate for more warm-up steps. then decays it with the cosine curve. Move the model to whatever device you're using. In training loop, set the model in training mode and make a progress bar. For each batch, move data to device, make a forward pass and then compute loss. Then make a backward pass to update weights. Once done, track running loss and accuracy of model and update progress bar. For validation data, iterate through each validation batch. Then similarly move data to device. Make a forward pass and then measure the validation accuracy and loss. This will print a detailed metric after each epoch. Now initialize a transformer with appropriate parameter according to the dataset, and values of like number of heads, depth of the network is taken from the paper. Now call the training function we made with the parameter required. It will take time and speed depends on specifications of the machine. I'm skipping the training process and jumping to final epoch. And see, the network converged to a good training and validation accuracy. Since Vision Transformer doesn't has its biases like CNN, it takes time to converge. If you increase the number of epochs, you can get a pretty decent result. Once training is done, you can make a function or directly take out and process the prediction to get the output. Put the model in eval mode, load the image to device and feed to the model. Use softmax function to get the probabilities of output and pick top k results. Now get index of maximum probability to identify the class in the class names. Now we can use the function with a sample image and its predicted frog. Let's see. The image is pretty low in resolution but still can see somewhat a frog, and our model is pretty confident though. Make sure you save the model to the disk. And one special thing about transformers which you will not get in regular CNNs is they can tell you which part of the image they focus on. I mean, you can plot attention map to see it. So let's make a function which takes model and input to plot attention heat map. Let's make a function to take care of this. Get the model, sample image, output from the last layer, first head, and device. Use eval mode and check the current device the model is running on and transfer the image on the same device. Get the prediction result and attention map. Now get the output from last layer and extract token by taking the first batch, first head, and all tokens except the CLS token itself. Assuming patches form n by n grid and add dummy dimension for image-like processing. Now get the height and width of the image and remove the first two dimensions from the attention map, converting it to pure 2D array. Now bring attention map from device to CPU and normalize the value between 0 to 1 to plot it as heat map. We have to plot the heat map over it as an overlay. And now traditional matplotlib things like make figure, plot image, plot attention map over it and set title, show the image and all. Now we can use this function to plot attention map like this. And this is the heat map plotted over the image, and the brightest area represents where the model put more attention than the coldest area or the lowest value. Congrats! You have just understood and made the vision transformer. Train it on your own dataset, play with architecture, just do whatever heck you want to do with it. The source code for this implementation is in the description, and don't forget to check out if you feel stuck. We'll meet in the next video again. Till then, thanks for watching.